Hello, everyone. I'm Cassandra, and I'm going to be starting my group presentation. For Project 2, we chose to do the buoyant force prompt. To start, I'll be covering what buoyancy is and what its buoyant force does. Buoyancy is an upward force that exists only when there is an opposing downward force on an object. Depending on the magnitude of that downward force, the object will either float or sink. Buoyant force is the resulting upward force when an object is submerged in a liquid. This force is dependent on the volume of the displaced fluid and the density of that fluid. Some similar concepts to buoyancy are density problems. This includes concepts like Archimedes' principle and light refraction. Archimedes' principle will be covered by Eric further in, so I will only be covering light refraction. Density is defined as the ratio of an object's mass to its volume. So, when light passes through a liquid, such as water, oil, and others, it reacts differently. The light will vary its direction depending on the index of refraction of the liquid at hand. This difference in behavior is what connects the two concepts. An object submerged in a liquid will either sink or float depending on the density of that liquid.
To understand how the idea of buoyancy came about, we first start with a question about floating objects. The question being, why do some objects float and other objects sink? To understand this phenomenon, buoyancy comes into play. So the ideas of buoyancy can be explained mostly using physics ideas that we should already be familiar with, particularly force. Recall that force is mass times acceleration. In the case of an object in water, there's a weight force pointing downwards. However, there's also another force pointing in the opposite direction, and this would be the buoyant force. This relationship is shown in the force diagram on the right. Just like always, we know that the net force is the sum of forces. So for a situation where an object experiences buoyancy, the buoyant net force would be equal to buoyant force minus the weight force. Notice that we're not adding, and the weight side is subtracted because it's in the opposite direction of the buoyant force. From the general equation, we can see that if the weight force is greater than the buoyant force, an object will sink. Whereas if the buoyant force is greater than the weight force, the object travels upwards. Of course, if the two forces are equal, the forces are considered balanced and the object won't move if it's not acted on by any other forces. So now we know the effect of buoyant force, but the question remains, what causes this buoyant force? This is described by the Archimedes principle, which states that buoyant force acting on an object is equal to the weight of the fluid it displaces. Now let's examine an equation describing this principle. We start with the buoyant force equal to the weight of fluid displaced. As a reminder of what fluid displacement is so that we can use it in an equation, recall that the equation for density is an object or material's mass divided by its volume. And since buoyancy is a force, of course there has to be some acceleration as well, which comes from gravity or g in our equation. Thus, our complete equation for the buoyant force would be Fb equals pvg, g being gravitational acceleration, v being volume, and p being density. So now we know what buoyancy is, how to calculate buoyancy, and how it affects objects. There's one more consideration that does come up. Suppose an object is partly submerged in water. The buoyant force would not directly act on the non-submerged portion of the object in this case. This means that for our buoyancy equations, we should make sure to only consider the portion of the object that is submerged. Mathematically, this can be thought of as the fraction of the object submerged times its total volume. The result of this can be subbed into our equation Fb equals pvg.
All right, now that we've gone over the basic principles of buoyancy, we can look at some real world applications in which buoyancy is observed or utilized. We decided to pick two pretty basic examples and fairly common applications for buoyancy. So we have a boat floating on the surface of water, as well as a hot air balloon rising. How it rises. All right. So for the boat example, much like an object on solid ground, both gravity and normal force keep the object at rest. The buoyant force pushes upward on the object and gravity pulls an object downward. And there's a certain relationship between the two that determines whether an object in water will sink or float. And to understand how this works, it's important to know how density plays its role in the equation here. The force of buoyancy equals the negative density times gravity times the volume. And so with that, you have your weight. And if your weight is equal to the buoyant force, the object will remain at rest. And if the weight of the object is greater than the buoyant force, the object will sink, obviously. And with when you have an object in water, you're only going to have about half of this boat in the water, maybe a third of it. And so the volume would only be a third of the boat. And you have gravity, which is 9.8 meters per second squared. But then your density changes here because the density of the boat above the water is going to be less than that of the density of it in the water. And as you go deeper into the water, the density of the water increases. So you have a boat that can float because the weight of the displaced water is going to be equal to that of gravity, or and if it's not, then the boat is gonna sink or rise, which doesn't happen because you can't displace more of the liquid than there actually is. And so we have a hot air balloon as well. And while you may think buoyancy can apply differently to a situation like a hot air balloon, the principles in the model will remain the same. And Archimedes' principle states that the buoyant force on a submerged object is going to be equal to the weight of the fluid that it displaces. So in the case of a hot air balloon, we have that the balloon will rise into the air because the density of the air inside the balloon is going to be warmer. And so it has a small, or the density is going to be smaller because the air inside the balloon is going to be warmer. And the air on the outside, the colder air, is going to be less dense because it's colder. And the balloon in the basket, it displaces a liquid fluid that is greater than the weight of the balloon in the basket. So it has a buoyant force acting upward on the system. And whether or not this upward force displaces gravity and allows for lift depends on different factors, such as the temperature inside the balloon and the temperatures outside the balloon as well. And the temperature is the main factor in this case because the density of air is dependent on the temperature. So, for example, the hot air balloon will fly better in the morning because the air outside the balloon will be cooler and it's going to be more dense. So then the hot air inside displaces it greater because of the weight on the outside is more. And the balloon can fly in warmer conditions, but the air inside the balloon must be much hotter than the air outside the balloon, and then you run into the risk of, burning the actual balloon. So that's why you don't really see balloons go out on a hot summer day, usually right in the morning. And but the force just needs to be enough for it to displace gravity. And with this, they take off, weight on the baskets or other weight that contributes to the actual weight of the balloon. So it can displace gravity and lift. And so that was just our real world examples and applications for hot air balloons. Thank you. We also have a works cited page where we just went over some different articles and we were able to piece together some stuff that helped us in this project. So thank you so much.